So I want you to just imagine for a second a standard space heater. The kind you might plug in under your desk during the winter.
Right, yeah, the little ceramic one.
Exactly. It pulls about 1,500 watts of electricity, and it pumps out enough heat to keep a small room comfortably warm.
Yeah, that makes.
Now, I want you to imagine taking 70 of those space heaters, turning them all on to their absolute maximum setting, and cramming them into a single cabinet that is roughly the size of your kitchen refrigerator.
And then you close the door.
Right. You close the door, and you expect whatever is inside that metal cabinet to not instantly burst into flames.
I mean, it sounds like a bomb at that point.
It really does. But that extreme, well, almost incomprehensible thermal density is the actual reality of the modern data center.
Yeah.
We're moving into an era where a single rack of computers generates so much heat that the tech industry is literally drawing up plans to build neighborhood-sized water towers just to keep the internet from melting.
It is a fundamental shift in the laws of physics that govern how we build our digital infrastructure. Like we are moving from an era of air conditioning to an era of heavy industrial fluid dynamics.
Welcome to today's deep dive. For you listening, our mission today is to decode exactly how we arrived at this tipping point, and more importantly, how the world's biggest tech companies plan to survive it.
Yeah, because the stakes are incredibly high right now.
Oh, absolutely. So we got our hands on a highly exclusive, deeply technical support document. It is titled the SuperCloud Composer Next Generation of Rack Scale Architecture 2026 Series Introduction. And it comes from Supermicro.
Right, and they are one of the primary architects of the physical hardware that makes up the cloud and modern AI systems.
Yeah, they build the actual metal. But at first glance, a document like this can be incredibly intimidating.
Oh, for sure. I mean, it is essentially an engineering roadmap intended for procurement officers and facility architects at hyperscale companies. Think the Microsofts, Googles, and Metas of the world.
Right, the companies buying servers by the warehouse load.
Exactly. It's filled with cooling specs, power distribution architectures, and software integration requirements. But what's fascinating here is if you look past the raw data, this isn't just a list of parts.
It's a declaration of the future.
Yes. By analyzing what they consider fully supported, what is currently in development, and what is being hastily planned for tomorrow, we get a completely unfiltered view into the physical reality of the artificial intelligence boom.
And we are going to rely on your expertise today to translate this blueprint from silicon to plain English. Because when you start peeling back the layers of this 2026 roadmap, you realize that building an AI supercomputer isn't just about writing smarter algorithms anymore.
Not at all. It's about orchestrating a massive physical symphony of metal, water, and electricity.
Right. Because the software intelligence that we all see on our screens, the chatbots, the image generators, the predictive models, that is just the tip of the iceberg.
It's just the interface. What this document reveals is the massive submerged industrial engine required to keep that intelligence running in the first place.
So to understand why a company needs to develop megawatt-scale water towers, we have to look at what they're actually stacking inside these buildings. And the first major section of this roadmap details the compute foundation.
The standard servers.
Right. And, okay, let's unpack this, because what immediately strikes you is the sheer scale and diversity of the hardware they have to support simultaneously. We aren't talking about a single type of server here.
No, not at all.
The document outlines support for massive arrays of Intel and AMD architectures spanning multiple generations. So they list the AS lines, the SSG lines, the SYS lines, all under these massive umbrellas of generation 12, 13, and 14 systems, all running side by side.
And that generational overlap is a crucial detail for anyone trying to understand enterprise technology. Because in the consumer world, when you buy a new laptop, you usually get rid of the old one.
Right. You trade it in or toss it in a drawer.
Exactly. But when you're operating a data center with 100,000 servers, you don't just rip out last year's hardware because a new chip was released. It's too expensive.
So you just rack the new generation right next to the old ones.
Yeah, you rack it right next to it.
Yeah.
The older generation 12 servers might be relegated to handling basic web traffic or internal file storage, while the brand new generation 14 servers handle the intensive database queries.
Which means the management software, this SuperCloud Composer, it has to act as a universal translator.
It does. It has to seamlessly monitor and deploy workloads across hardware that might be 3 or 4 years apart in technological evolution.
But as I was reading through this huge matrix of supported standard compute servers, There was a specific metric attached to all of them that really caught my eye.
Oh, the support coverage percentage.
Yes. The document explicitly states support coverage 95%. The other 5% will be provided upon customer request, and I really want to interrogate that.
It's an interesting philosophy.
Right, because if you are selling enterprise-grade data center management software, isn't the goal total absolute compatibility? I mean, admitting you only cover 95% out of the box feels like leaving a massive amount of money on the table. Why would a massive tech company stop at 95%?
Well, it might seem like a weakness, but it is actually a reflection of the Pareto principle applied to silicon. And honestly, it makes perfect engineering sense.
How so?
The 95% represents the standardized, off-the-shelf reality of modern data centers. The vast majority of global enterprise workloads, whether that's hosting millions of WordPress sites, running standard payroll databases, or streaming video, they operate perfectly on highly optimized, predictable, cookie-cutter server configurations.
So the boring stuff,
Yeah.
the everyday internet.
Right, the everyday internet. Supermicro is saying their software completely automates and manages that 95% without a human ever needing to intervene.
Okay, so they nail the mass market. But then who is the 5%? Like, if the standard servers handle everything from Netflix to corporate payroll, what kind of company requires a server so unusual that it breaks the standard management software?
Think about organizations pushing the absolute boundaries of physics and time. A prime example would be a high-frequency trading firm in Chicago or New York.
Oh, right where milliseconds matter.
Milliseconds are too slow. In that world, an advantage of a single microsecond can be worth millions of dollars. So they might require a deeply customized server where the network interface card is physically soldered closer to the processor, just to shave off a nanosecond of signal travel time.
Wait, literally just reducing the physical distance the electricity has to travel on the board?
Yes. Or they might demand that all standard background management chips be completely stripped out so that nothing interrupts the CPU's focus on their training algorithms.
So it's the technology equivalent of a Formula One race car. You know, you strip out the air conditioning and the radio because you only care about raw speed. But as a result, a standard mechanic can't just plug a diagnostic tool into it anymore.
Exactly. It's totally custom. Another example would be a national laboratory running classified nuclear decay simulations.
Wow.
Yeah, they might require a completely bizarre ratio of memory to compute that no commercial business would ever use. By explicitly carving out that 5% Supermicro isn't showing weakness, they're signaling to those elite clients that they have the deep engineering bench required to write custom software hooks for those bespoke configurations.
So it's essentially saying we've mastered the standard road, but if you want to drive off a cliff, call us and we'll build you a parachute.
That is a perfect way to put it.
That makes total sense. And it isn't just standard Intel and AMD x86 processors on that road anymore. The document places a huge emphasis on supporting Ampere platforms, specifically the ARS lines.
Yeah, the ARM-based systems.
Right. And for you listening who might not track semiconductor architecture, Ampere uses ARM-based processors. Now, for the longest time, ARM was strictly the domain of smartphones because it is incredibly power efficient, but it just didn't have the heavy lifting capability of traditional data center chips.
Right. It was great for battery life, but not for enterprise workloads.
Exactly. So the fact that ARM architecture is now a massive native part of this hyperscale roadmap and shares that same 95% support rule, it just seems like a watershed moment.
It is a massive shift. The hyperscalers, the people buying servers by the tens of thousands, they've realized that power efficiency is now just as important as raw speed.
Because of the electricity costs.
Yes, if you have a massive array of servers that just need to do millions of tiny, simple tasks like routing internet traffic or serving up simple web pages using a massive power-hungry traditional processor is like using a sledgehammer to drive in a thumbtack.
It's just a massive waste of energy.
Exactly. ARM processors give them the ability to pack incredible density into a rack while drawing a fraction of the electricity. It proves that the data center of the future is fundamentally heterogeneous. It is a mix of heavy lifters and highly efficient marathon runners, all orchestrated by the same software.
And we can see exactly where that evolution is heading because of one specific line item in the compute section. Beneath all the fully supported Generation 14 hardware, there is a listing for Generation 15 platforms, but its status just says developing.
And if we connect this to the bigger picture, that single word reveals the hidden timeline of the tech industry.
How do you mean?
Well, in the hardware world, physical silicon takes years to design, test, and fabricate. Right now, Generation 14 is the cutting edge that you can actually buy and rack up. But the physical chips for Generation 15 are already sitting in secure labs.
But what I find fascinating is that they are listing unreleased hardware in a software management document. I would have assumed you finish building the server first, and then you figure out how the software is going to talk to it.
That used to be the case. But the scale of modern deployments makes that sequential approach impossible now. If you wait for the hardware to be finished before you write the management software, you will be a year behind the market.
So they have to do it at the same time.
Total lockstep. They're laying down the digital tracks just a few feet in front of the speeding hardware train. When Generation 15 physically ships, the SuperCloud Composer software has to be completely ready to monitor its temperature, deploy operating systems to it, and balance its workloads on day one.
Wow. Which brings us back to the sheer physical reality of all this compute power. We're talking about packing thousands of Generation 14 servers, heterogeneous ARM processors, and hyperdense blade systems into these windowless concrete buildings.
A lot of metal in one room.
A lot of metal. And as you pack more and more of these highly advanced processors closer together, mostly to speed up the network, you run face first into the most terrifying physical bottleneck in the entire technology sector.
Heat. It is the ultimate enemy of computation.
And this logically brings us to the second part of our deep dive, the physics of the data center. Taming the heat. Because for a long time, the solution was relatively simple, right?
Yeah.
You walk into a traditional data center and it is deafeningly loud because it is filled with thousands of high-speed fans.
Right, massive air movement.
Yeah, you pump heavily air-conditioned air into the front of the server rack. The fans pull that freezing air over the hot components and hot air blasts out the back into a return duct.
But as I read the cooling section of this 2026 roadmap, it is clear that air cooling has hit a brick wall. We aren't talking about simple fans anymore. No, we are moving firmly and aggressively into liquid cooling.
Like, I keep thinking about this analogy. This isn't about pointing an AC unit at a hot gaming rig. This is about industrial thermodynamics.
It really is. And I understand why air is no longer sufficient. We have to talk about the physics of thermal density. Air is actually a remarkably poor conductor of heat. Yeah, its specific heat capacity, which is the amount of energy required to raise its temperature, is very low. When server chips were drawing maybe 100 or 200 watts of power, blowing cold air over a metal heatsink was fine. The air could absorb that heat and carry it away.
But the chips have changed.
Drastically. A modern high-end processor, particularly the ones used for artificial intelligence, can draw 700 to over 1,000 watts of power individually.
Just one chip.
Just one chip. If you try to cool a 1,000-watt chip with air, the air physically cannot absorb the thermal energy fast enough. The heat will build up on the silicon faster than the air can carry it away, and the chip will literally melt its own microscopic circuitry in a matter of seconds.
So it destroys itself before the air even has a chance to help.
Exactly. Liquid, on the other hand, specifically water or engineered coolants, is exponentially more efficient. By volume, water can absorb roughly 4,000 times more heat energy than air.
Wait, 4,000 times. That puts it into perspective, which explains the hardware they are deploying to manage this. The expert document lists fully supported cooling distribution units, or CDUs. There are in-row CDUs, which sit at the end of a line of servers, but the ones that really highlight the scale are in-rack CDUs.
Right, the ones built right into the cabinet.
Yeah. The document explicitly supports a 100 kilowatt in-rack unit and then details massive 250 kilowatt units available in both EIA and OCP formats.
So a cooling distribution unit, or CDU, is the mechanical heart of the liquid cooling system. It is a massive industrial pump and heat exchanger system.
Okay.
It pumps cold liquid directly into the server chassis through microscopic channels right on top of the processors, and then pumps the boiling hot liquid out to be cooled down. When the document says 250 kilowatt in-rack, it means a single server cabinet, again roughly the size of a refrigerator, is generating 1/4 of a megawatt of heat.
That brings me right back to the space heater analogy from the beginning. A single cabinet producing 1/4 of a megawatt of heat is staggering. But there's a transitional technology listed here that I want to dissect. It's called an RDHX, or a rear door heat exchanger.
Those are fascinating.
Yeah, the document lists 50 kilowatt and 80 kilowatt doors as fully supported. How does that work?
So rear door heat exchangers are a brilliant feat of engineering designed for data centers that are caught in the transition between air and liquid. Tearing out your entire air-cooled infrastructure to plumb liquid directly to the chips is incredibly expensive and disruptive.
Right, you'd have to shut the whole building down.
Exactly. So instead of bringing liquid to the processor, you bring it to the edge of the rack. And RDHX literally replaces the back door of the server cabinet with a massive liquid-filled radiator.
So the servers still use their internal fans to blow the hot air away from the chips.
Correct. The servers operate as if they are air-cooled. They blast the hot air out the back. But before that scorching air can escape into the data center and overwhelm the room's air conditioning, it has to pass through this massive radiator door.
And the water absorbs it all.
Yes, the liquid inside the door absorbs all the thermal energy, and the air that finally steps out into the room is remarkably cool. It neutralizes the heat at the source without requiring you to plumb water directly over the fragile electronics.
It's a fantastic hybrid step, but as I was reading the specs for these radiator doors, I noticed a contradiction that I really have to push back on.
Okay, what did you find?
The document lists a 50 kilowatt 52 U rear door heat exchanger as fully supported. It's ready to go, but literally right beneath it, there's another 50 kilowatt rear door unit, and its status is listed as developing. Why reinvent a 50 kilowatt door if they already have one that works perfectly fine? The raw cooling capacity is identical.
That is a great catch. And it highlights a fundamental truth about industrial engineering. Raw capacity is only one part of the equation. Just because two machines handle the same wattage doesn't mean they do it with the same efficiency or in the same physical footprint.
Okay, so it's about form factors and generational shifts.
Yes. When you see a new product with identical capacity marked as developing, it almost always indicates a radical shift in standard dimensions or efficiencies, even if the raw wattage remains the same.
Let me propose a theory on this. Could it be about the pressure of the liquid? If you have an older data center, the internal plumbing might not be able to handle the high pressure required to push water through the current 50 kilowatt door. Is it possible the new developing model achieves the same cooling but requires a significantly lower water pressure, meaning older facilities can use it without blowing their pipes?
That is highly likely. Fluid dynamics in a data center is a nightmare of pressure drops and flow rates. If Supermicro can design a radiator that offers 20% less resistance to the water flow, the data center can use smaller, cheaper pumps, which saves massive amounts of electricity at the facility level. Alternatively, the new door might be dimensionally thinner, allowing facilities to use slightly longer servers in the same aisle space. In the hyperscale world, optimizing a piece of hardware to save an inch of space, or a fraction of a psi, in pressure across 10,000 racks, result in millions of dollars in savings.
So it's the difference between a muscle car engine and a modern hybrid engine. They might both produce 300 horsepower, but the hybrid does it using half the fuel and fits in a much smaller space.
Precisely. The evolution of infrastructure is rarely about just making the number bigger. It's about making the delivery of that number more elegant and cost-effective.
Well, speaking of making numbers bigger, here's where it gets really interesting, because we have to talk about the extreme end of the roadmap. This is where the document stops being a standard catalog and starts looking like actual science fiction.
The mega coolers.
Yes. At the very end of the cooling section, it outlines the facility-level hardware. It lists a 1 megawatt water tower marked as developing, and right next to it, a dry tower marked as planning.
We really need to pause and truly internalize the scale of a 1 megawatt cooling tower.
I looked this up to try and ground it in reality. A megawatt of continuous power consumption is roughly what it takes to run 700 to 800 standard American homes. Imagine the electrical grid for an entire suburban neighborhood.
Right.
Now imagine every single watt of that electricity being consumed and converted instantly into pure radiating heat. You have to remove an entire neighborhood's worth of heat from a single building constantly, 24 hours a day.
And the distinction between a water tower and a dry tower tells us a lot about the geopolitical and environmental pressures facing these tech giants right now.
Because of the water usage.
Exactly. A traditional water tower, or an evaporative cooling tower, is incredibly efficient. It uses the evaporation of water to reject heat into the atmosphere. But that efficiency comes at a massive environmental cost. These towers can consume millions of gallons of fresh water every year.
Which is becoming a massive point of friction. I mean, we are seeing communities push back hard against data centers moving into their towns because the data center threatens to drain the local municipal water supply.
Exactly. And that is why the dry tower is in the planning phase. A dry tower operates more like the radiator on your car. It uses a closed loop of liquid. The hot liquid comes out of the data center, runs through massive coils outside, and gigantic fans blow ambient air over the coils to cool the liquid before it returns inside. It consumes absolutely zero water.
But I'm guessing there is a catch.
The catch is that dry towers are significantly less efficient, especially in hot climates. If you build a data center in Arizona, blowing 100-degree ambient air over a dry tower radiator isn't going to cool your servers down very well. You have to use massively powerful fans, which means you are spending a fortune on electricity just to run the cooling system.
So they have to support both.
Right. The fact that SuperCloud Composer is building software hooks to manage both massive evaporative towers and closed-loop dry towers tells us they are preparing for a fractured global landscape. A world where local climate, water scarcity laws, and environmental regulations will dictate exactly how you are allowed to cool your systems.
But this raises a glaring question. If we look back at the standard servers we discussed at the beginning, the Intel and AMD Generation 14 systems, even a massive rack of those does not require a megawatt of cooling. A 1 megawatt water tower is absolute overkill for standard cloud computing, so why are they building it?
They are building it because of what is outlined in the very next section of the document. Standard computing is plateauing. The only reason a facility architect demands megawatt-scale, liquid-cooled infrastructure integrated directly into their management software is because they are clearing space on the floor for the AI SuperCluster.
The bleeding edge. This section of the 2026 roadmap is absolutely the crown jewels of the document. It details the precise hardware ecosystems for the most advanced artificial intelligence supercomputers on the planet, and it methodically lays out the specs for two massive monolithic systems, the GB200 NVL72, and its successor, the GB300 NVL72.
Now, for anyone who doesn't track semiconductor naming conventions, GB stands for Grace Blackwell. That is NVIDIA's absolute top-tier, world-dominating AI architecture. It pairs their Grace CPU with their Blackwell AI GPU, and NVL72 refers to the NVLink configuration.
Explain NVLink, because I think a lot of people assume an AI supercomputer is just 1,000 graphics cards all doing their own math and sending the answers back to a central boss. But NVLink changes that dynamic entirely, right?
It changes the very definition of what a computer is. In a traditional setup, if chip A needs data from chip B, it has to send a request over a standard network cable. That takes time, maybe a few milliseconds.
Which is too slow for AI.
In the world of training massive AI models, a millisecond is an eternity. It creates a massive bottleneck. NVLink is a proprietary hyperspeed networking fabric created by NVIDIA. In an NVL72 configuration, you have 72 incredibly powerful GPUs connected with such massive bandwidth that they can all access each other's memory instantly.
So they act as one.
Exactly.
Yeah.
From the perspective of the software running the AI model, it doesn't see 72 individual graphics cards in a rack. The NVLink fabric tricks the software into seeing one single gigantic unified megachip.
It is the ultimate hive mind. And the document lists the exact components required to build this hive mind. Let's look at the GB200 ecosystem first. It features a specific compute tray, the ARS-121GL NBO LCC. It uses a specific NVLink switch to connect all those brains together, the SSE NVL72 SWN5200. And for power delivery to this monster, the document specifies power shelves from two vendors, Lite-On and Delta. And as we discussed, it explicitly notes this entire rack requires a 250 kilowatt liquid cooling unit.
The GB200 is the current state of the art. It is the system that massive AI startups and hyperscalers are spending billions of dollars right now trying to acquire. But this is a 2026 roadmap, which is why the entry right below it is so fascinating.
The GB300, the successor. The compute tray gets a bump up to a new model, the NB3 LCC tray. The NVLink switch is upgraded to the N5500, which presumably offers even more bandwidth between the 72 chips. But there is a subtle change in the vendor list that I want your take on. For the GB200, the power shelves were provided by Lite-On and Delta, but for the GB300, Supermicro is now listed alongside Lite-On and Delta for the power shelf. Why the sudden shift into manufacturing the power delivery themselves?
It is a textbook example of vertical integration driven by risk mitigation. Historically, Supermicro is famous for building the metal chassis, designing the complex motherboards, and assembling the compute nodes. Power delivery was something you outsourced to specialists like Delta.
Right, let the power guys handle the power.
Exactly. But as the power requirements for a single rack hit 1/4 of a megawatt, the power shelf is no longer a generic accessory. It is arguably the most critical point of failure in the entire system.
Let me guess. If a third-party power shelf fails, it doesn't just turn the machine off. It could physically damage millions of dollars of silicon.
Exactly. When you're dealing with a single rack of GB300s that likely cost as much as a small private jet, you cannot afford to have a minor voltage fluctuation from a third-party power supply ruin a multi-million-dollar AI training run.
Wow, so they just built it themselves to be safe.
By heavily investing in R&D to build their own power shelves, Supermicro is taking control of the entire hardware stack. They are ensuring that the power delivery is perfectly flawlessly synchronized with their motherboards and the liquid cooling pumps. It allows them to guarantee reliability at a level you simply cannot achieve when you are piecing together parts from 5 different vendors.
But despite the massive hardware upgrades between the 200 and the 300, what's interesting is the software features required to manage them remain identical in the document. Both systems explicitly list support for monitoring device health status event alarm, leak protection firmware upgrade, advisor, and logging.
Because fundamentally, the operational hygiene of a supercluster doesn't change from generation to generation. The orchestration software still needs to verify that the firmware is secure, that the processors aren't overheating, and that the events are being logged.
Right.
However, out of that list of standard IT management features, there is one that is completely unique to the liquid-cooled AI era, and its importance cannot be overstated.
Leak protection.
Yes.
I want to dive deep into the mechanics of this because I was thinking about it. When you have 250 kilowatts of liquid cooling running next to a GB300, supercluster leak protection isn't just a nice-to-have software feature, it's mission-critical. In a traditional data center, if someone said we have a leak, it meant a chilled water pipe in the ceiling was dripping onto the floor, and a facilities guy with a mop and a bucket had to go deal with it. It was a plumbing issue. But in a GB300 supercluster, the water isn't in the ceiling.
No, the water is inside the server. It is being pumped through microscopic copper cold plates that sit literally millimeters away from the most advanced electrically dense silicon on Earth.
Which means leak protection has to be an automated, instantaneous defense mechanism.
The mechanics of it are incredibly intense. The compute trays have specialized moisture sensors and pressure sensors built right into the plumbing loops. If a fitting vibrates loose and a single drop of conductive coolant escapes, or if the pressure in the line drops by a fraction of a percent indicating a microfracture, the SuperCloud Composer software has to react faster than humanly possible. Within milliseconds, the software has to execute a complex sequence of events.
What does that sequence look like step by step?
First, it has to instantly isolate the power. It cuts the electricity to that specific compute tray to prevent a catastrophic short circuit that could arc and destroy the adjacent servers.
Okay, shut the power down.
Second, it sends a command to the Interact CDU to immediately close the local coolant valves, isolating the leak so it doesn't drain the entire cooling system into the server chassis.
Just trap the water.
Right. And third, it has to signal the overarching AI job scheduler that a node has gone dark, forcing the software to instantly reroute the mathematical workload to another healthy rack so the AI training model doesn't crash entirely. All of this happens before a human operator even has time to blink. It is high-stakes digital plumbing, and it requires software that is absolutely bulletproof.
That is genuinely terrifying to think about. You have this massive roaring machine, and it's constantly balancing on the knife edge between peak mathematical performance and total electrical destruction managed by a few lines of leak detection code. Now, keeping with the theme of things that are terrifying, we need to talk about the final entry in this AI SuperCluster section.
Oh, the VR200.
Yes, the VR200 mystery. It almost reads like a classified leak that someone forgot to redact. Listen to the clues provided in this document. The compute tray is listed as an ARS-122GLR2ALC. Its status is not supported. It's not even developing. The status simply says planning. Next to it is a note that says access info will be provided next week. And then the wildest part, it lists a specific target. It says Plan P up C in 3.14.
Right. POC meaning proof of concept.
Yeah.
The physical prototype.
Right. So I want you to put this into perspective for us. What does a timeline of POC in 34141, which we can safely assume means March of 2026, tell us about how fast this world moves?
It tells us that the traditional rules of technology development have completely disintegrated.
What were the old rules?
Well, in the past, developing a new rack-scale architecture was a methodical multi-year process. You spent a year in the planning phase, then you spent a year in development testing thermal tolerances and electrical routing. Then you built a proof of concept. What this entry reveals is a hyper-accelerated R&D cycle driven by pure, voracious demand. You have a document stating that the system is only in the planning phase. The engineers haven't even been given the access credentials yet. They get them next week, and yet management is demanding a physical working proof of concept by March.
It's like an airline executive telling their engineers, I know you haven't seen the blueprints for this new jet engine, yet you'll get them on Monday, but I need a working prototype on the runway in 3 months. It is literally building the airplane while it is in a nosedive.
It perfectly illustrates the panic and the pressure in the AI industry. The hyperscalers, the ones spending billions, they are demanding the next generation of hardware before the current generation has even been fully delivered. They know that whoever has the most compute power wins the AI race, full stop. So Supermicro and NVIDIA are forced to compress years of development into months. And crucially, SuperCloud Composer, the software team, has to somehow write management code for a machine that literally does not exist yet.
Wow, they're coding blind.
They're writing telemetry hooks based on theoretical CAD drawings, hoping that when the VR200 prototype is finally bolted together in March, their software will actually be able to turn it on.
That is wild. And all of this, the current GB200s, the impending GB300s, the mysterious VR200 prototypes, and the megawatt water towers required to keep them from melting, they are all incredibly, unbelievably hungry for electricity. Where do they get their juice?
That brings us logically to the nervous system of this entire operation, power infrastructure.
And the power delivery is arguably the most complex logistical challenge facing the AI rollout today. We are moving from data centers that require 10 or 20 megawatts of total power to facilities that are demanding hundreds of megawatts, sometimes a full gigawatt.
Let's look at how this document addresses the distribution of that power within the facility. It lists the supported PDUs, or power distribution units. For those listening, a PDU is essentially a highly intelligent industrial-grade power strip that routes the main facility power down to the individual servers. What struck me about this section is the massive, diverse ecosystem of vendors that SuperCloud Composer explicitly supports. We have Raritan, specifically their high-end PX3 series. We have Schneider Electric with a massive list of supported ePDU and AP models. We have Servertech, and we have Eaton. This raises an important question, doesn't it? Why is Supermicro spending so much software engineering time making sure they perfectly support 4 different rival power distribution brands? I'm curious what your theory is on this. Why wouldn't they just force everyone to use Supermicro PDUs?
I have to assume it's entirely about removing friction from the sales process. You know it's about avoiding vendor lock-in. If you are trying to sell $100 million worth of AI servers to a massive global bank, and that bank has spent the last 15 years standardizing all their data centers on Schneider Electric power infrastructure, they're not going to rip all that out just to accommodate your servers.
Exactly. It is a strategic masterstroke in enterprise software. SuperEcho knows that data centers are highly entrenched environments. By ensuring that SuperCloud Composer can natively communicate with Raritan, Schneider, Servertech, and Eaton, they are neutralizing a massive objection from the customer's facilities team.
They can just slide right in.
They are saying, you don't need to change your electrical infrastructure. Keep the PDUs you know and trust. Our software will seamlessly plug into them, monitor their voltage drops, and manage their power loads as if we built them ourselves. It turns the management software into a universal adapter. By supporting 4 major PDU brands comprehensively, SuperCloud Composer is positioning itself as a universal manager, not a closed ecosystem.
So they are playing incredibly well with others on the distribution side, but then we look at the shelves and grids, the power shelves and the backup systems. And things get very interesting. The document looks at the power shelves and lists them as fully supported, but versus that the BBU shelf, the battery backup unit, is only listed as planning. And I have to push back on this. You just emphasized how critical power is. You noted that a power fluctuation could ruin a multi-million-dollar AI training run. If power is so important for AI, why is the battery backup shelf only in the planning stage? Shouldn't a local battery backup unit be the very first thing you engineer and fully support?
It seems completely counterintuitive, doesn't it? In traditional server architecture, local battery backup was the ultimate safety net. You always put a heavy lithium-ion or lead-acid battery unit at the bottom of the rack. If the city grid went down or the facility lost power, that local battery would instantly take over and keep the servers running for the 5 or 10 minutes it took for the massive diesel generators out back to spin up and take the load.
Right. It bridges the gap.
But you have to contextualize the lack of in-rack batteries with the raw numbers we discussed earlier.
Yeah.
A single GB300 AI rack pulls over 200 kilowatts of power.
I see the physics problem now. If you try to power a 200 kilowatt load with a local battery, I mean, how long would a standard rack-mounted battery even last?
Seconds. Literally seconds. The sheer volume of energy being consumed is too vast. To bridge a 5-minute power gap for a single AI rack, you would need a battery the size of a minivan. You physically cannot fit the necessary chemical storage inside the server cabinet. It's too heavy, it takes up too much valuable space that should be used for compute, and cramming massive lithium batteries next to boiling hot processors is a fire hazard of catastrophic proportions.
So if they aren't putting the batteries in the rack, how do they survive a power flicker? The document offers a clue. Right beneath the delayed battery backup unit, there is an entry for something called the Power Grid Manager, and its status is developing.
And that is the paradigm shift. Rack-scale architecture is moving away from just keeping batteries in the rack toward intelligent, software-defined facility power grids that route electricity dynamically.
Explain how a software-defined power grid replaces a battery.
Instead of relying on a local battery to muscle through a power failure, the software manages the entire facility's electrical load dynamically in real time. Let's say the local city grid experiences a sudden drop in voltage. The Power Grid Manager detects this instantly. Instead of switching to an in-rack battery that doesn't exist, the software instantaneously throttles down the computing power of the AI clusters.
It slows them down.
It tells the processors to run at 50% capacity, immediately halving the power draw of the entire building. It might completely pause non-essential data processing jobs, essentially load-shedding the facility in milliseconds. By dynamically shrinking the building's total power consumption, it allows massive facility-level UPS systems, huge battery rooms physically separated from the servers, to easily absorb the shock and keep the critical AI runs alive until the generators kick in.
That is wild. Let me try an analogy here to make sure I've got this. It's like a smart city electrical grid during a massive summer heat wave. The grid operators know they don't have enough power to run everything. So instead of letting the entire city black out the smart grid, dynamically dims the streetlights, slightly reduces the voltage to residential areas, and temporarily pauses industrial manufacturing plants, all to ensure that the hospitals and emergency services never lose power. The Power Grid Manager in this software is doing the exact same thing, but instead of hospitals and streetlights, it's prioritizing multi-million-dollar AI training clusters over standard web servers.
That is a perfect analogy. The software becomes the safety net. But I want to pause and reflect on what we've covered so far. We are talking about managing 95% of server types, multiple megawatt cooling systems, orchestrating unreleased NVLink AI superclusters, integrating with cross-vendor power grids, and dynamically throttling a facility's power to survive a blackout.
It's an impossible amount of variables. I mean, managing all of this is impossible for a human with a clipboard. You need a massive software layer.
Exactly. The scale and speed of these physical systems have surpassed human reaction time.
Which brings us to our final section, the brain. The SuperCloud Composer software features. We spent a lot of time on the brutal physics of the hardware, but now we need to unpack the software brain that orchestrates it all.
This is the conductor of the orchestra. It's the central nervous system that brings all the disparate organs together into a living, breathing entity.
Let's start with the basics listed in the document: the dashboard and deployment. The software natively supports a standard dashboard OS deploy and baseline configuration management.
All right, those are the table stakes. Any IT management software built in the last 2 decades has to have a dashboard where you can see if a server is online or offline, and it has to allow an administrator to remotely deploy an OS, like Linux or Windows, onto a bare piece of metal. It's foundational.
But the document quickly moves past the basics and dives into advanced telemetry. Specifically, it lists GPU performance metrics, health status, and event alarms. And I want to focus on that first one.
GPU performance metrics, being a native fully supported feature, proves this software is purpose-built for the AI era. 10 years ago, a data center management tool cared about 3 things. Is the CPU overheating? Are the fans spinning? And are the hard drives failing? Graphics processing units, or GPUs, were a niche afterthought used for rendering video or virtual desktops. The fact that GPU performance metrics are now elevated to a primary telemetry feature tells you that the GPU is now the center of the universe.
And what specifically are they monitoring? I assume it's more complex than just checking if the graphics card is turned on.
Immensely more complex.
Yeah.
An AI supercluster relies on specialized components within the GPU. The software isn't just checking the temperature, it is likely monitoring tensor core utilization.
Okay, explain tensor cores for the listener who might just know standard CPUs.
The standard CPU is a generalist. It can do a wide variety of tasks reasonably well. A tensor core is a highly specialized piece of silicon built entirely to do the specific type of matrix math required for artificial intelligence, and to do it at blinding speed. It's like the difference between a Swiss Army knife and a surgical scalpel. SuperCloud Composer is monitoring exactly how efficiently those scalpels are cutting data. Furthermore, it's monitoring the NVLink bandwidth saturation, meaning is the network fabric connecting the 72 chips getting clogged up with too much data. And it's monitoring HBM, or high bandwidth memory bottlenecks.
Let me guess on HBM. High bandwidth memory is when they stack the memory chips vertically like a skyscraper right on top of the processor, so the data physically has a shorter distance to travel, which speeds everything up.
Precisely. If the tensor cores are starving for data because the HBM is bottlenecked, the multi-million-dollar machine is wasting time and electricity. The orchestration software has to monitor all these incredibly microscopic specialized AI metrics in real time across thousands of chips and display it on a dashboard so operators can optimize the workloads.
But with that level of deep granular control over an entire building's worth of supercomputers, security becomes an existential concern. The document outlines a robust suite of security and access control features. It lists support for user management via RBAC, LDIP, keycloak integration, and strict account lockout policies. Let's break those down because security at the scale isn't just about having a strong password.
Security at this level of infrastructure is primarily about access control. The blast radius of a single mistake is simply too large. RBAC stands for Role-Based Access Control. Imagine you have a junior intern, a thermal engineer, and a senior network architect all logging into the same SuperCloud Composer dashboard. You absolutely cannot give them the same permissions.
Because if the intern accidentally clicks the wrong button, they could shut off the liquid cooling to a GB300 rack and destroy it.
Exactly. With RBAC, the intern is granted a role that only allows read-only access to the dashboard. They can look at the graphs, but they can't click anything. The thermal engineer is granted a role that only allows them to adjust the pump speeds on the cooling distribution units. They can't see the AI workloads or touch the network switches. The network architect can manage the NVLink fabric, but can't touch the cooling. It forces hyper-granular compartmentalization.
And what about LDAP and keycloak?
Those are enterprise identity management integrations. In a massive company with 10,000 employees, people are constantly being hired, fired, or changing departments. If a disgruntled systems administrator is fired at 2 p.m. show, you cannot rely on someone manually going into 50 different software systems to delete their accounts. Keycloak and LDAP act as a central source of truth. The moment HR marks that employee as terminated, their access to the entire global SuperCloud infrastructure is revoked instantly worldwide, preventing any malicious sabotage.
That makes perfect sense. It centralizes the authority. Now, beyond human access, the software has to talk to other software. The API and enterprise integration section is fascinating. It details support for a RESTful API and SNMP gateway, and specifically calls out webhooks that integrate directly with enterprise platforms like ServiceNow and Salesforce.
The webhooks are where the real operational magic happens. This is how you automate incident response at massive scale.
I have a biological analogy for webhooks that I think perfectly explains their function. I look at webhooks as the equivalent of a reflex arc in the human nervous system.
I like where this is going.
If you accidentally touch your hand to a hot stove, your spine pulls your arm back before the pain signal even reaches your brain. It bypasses conscious thought because the danger is too immediate. The webhooks in this software seem to operate the exact same way. If a 250 kilowatt in-rack CDU springs a microscopic leak, SuperCloud Composer doesn't just sound an alarm on a dashboard and wait for a human operator to notice it and decide what to do. The webhook reflexively fires a payload of data. It automatically and instantaneously opens a high-priority incident ticket in service mode. Now it dispatches an alert to a facilities engineer's phone with the exact physical coordinates of the rack, and it might even log an automated hardware replacement order in Salesforce. It completely automates the human out of the loop for the initial crisis response.
That is exactly the architecture, and the reflex arc is the perfect way to visualize it. Because at RAG scale, human reaction time is functionally obsolete. If you wait for a human to notice a flashing red light and manually type out a support ticket, the server's already melted and you've lost the hardware. The machine has to instinctively talk to the business operations software directly.
But for all the things this software can do perfectly, the leak detection, the webhooks, the role-based security of the document, acknowledges that the brain is still evolving. There's a developing frontier here of features that aren't fully baked yet. Syslog, export power grid management, and thermal protection policy are all listed as developing. And I have a massive question about this last one. We saw leak protection was fully supported, finished, and working back in the AI section. Why is thermal protection policy still developing? They both relate to keeping the machine safe from the cooling system, right?
It comes down to the staggering difference in mathematical complexity. I'll break down the difference between a binary event versus a dynamic policy. A leak is fundamentally a binary event. Is water leaking, yes or no? If the sensor reads yes, you trip to the breaker, shut the valve, and fire the webhook. It is a highly critical but mathematically simple logic gate.
Like breaking a laser tripwire, you either cross it or you didn't.
Precisely. But a thermal protection policy, that is not binary. That is a wildly dynamic, continuously evolving, multidimensional physics problem. Managing thermal policies across hundreds of thousands of cores and dynamic RDHX cooling systems that all share a single 1 megawatt evaporative water tower requires predictive algorithms that are still being perfected.
Because it's not just reacting to heat, right? It has to predict the heat.
Exactly. If you wait until a GB300 chip registers as dangerously hot before you tell the pump to send more cold water, you are too late. The thermal mass of the system takes time to react. A true thermal protection policy requires predictive algorithms. The software has to look at the job scheduler and realize, okay, a massive, highly intensive AI language model training run is scheduled to start on rack sector A in exactly 5 minutes. Based on historical data, that sector will experience a massive thermal spike. The software must proactively ramp up the pump speed in the liquid CDUs right now. It must increase the fan speed on the dry cooling towers outside the building right now to pre-cool the massive volume of liquid before the thermal wave even hits the silicon.
Wow. So it's essentially playing 4D chess with fluid dynamics.
Right.
It's moving the cooling pieces into position before the heat even arrives.
Yes. It is combining predictive workload scheduling, thermodynamics, and facility-level power management into a single, unified algorithmic response. It is incredibly mind-bendingly complex to code safely. If the algorithm precurs the system too aggressively, you waste massive amounts of electricity running pumps unnecessarily. If it underestimates the thermal spike, the chips throttle themselves or melt. That is why it is still listed as developing. They are still perfecting the incredibly delicate algorithms required to keep a modern data center perfectly balanced on the razor's edge between maximum computational performance and catastrophic thermal runaway.
So what does this all mean for you, the listener? I think that captures the sheer gravity of this entire roadmap. This document isn't just a list. It is a declaration that the future of computing these superclusters mega cooling systems requires an orchestration layer like SuperCloud Composer capable of speaking to everything from a Raritan PDU to a GB300 NVLink switch. We have gone from the vast arrays of standard x86 servers that run the mundane internet through the industrial plumbing of quarter-megawatt liquid coolers and hybrid radiator doors. We've peered inside the monolithic NVLink superclusters, mapped the transition to software-defined, smart power grids, and dissected the predictive reflexive digital brain trying to orchestrate it all.
It really shatters the illusion of the cloud as this weightless abstract thing. The cloud is heavy, brutal, and deeply industrial.
And to leave you, our listener, with a final provocative thought to mull over or explore on your own. We saw today that the AI superclusters are demanding megawatt water towers and dynamic power grids while thermal protection policies are still in development.
Right? The physical demands of artificial intelligence are pushing infrastructure to its absolute breaking point.
Exactly. So as we march toward the PPO-C dates and the rollout of the X15 generation over the next few years, the central question for you isn't whether NVIDIA or AMD will design chips smart enough to run the next iteration of AI.
The real question is whether our physical infrastructure, our power grids, and our cooling systems will be smart enough and fast enough to keep those brilliant chips from melting themselves into slag.
From the murky living architecture of the modern data center back to the brutal binary reality of thermodynamics, either you cool it or it burns. Thank you so much for joining us on this deep dive into the blueprint of our digital future. Keep exploring, keep questioning how the massive invisible systems around you actually work, and we will catch you on the next one.